And hello from the campus of Carnegie Mellon University in Pittsburgh, Pennsylvania. We welcome you to today's SEI webcast, ensuring the safety and security of AI systems. My name is Shane McGraw. I'm the Outreach Manager here at the Software Engineering Institute, and I'd like to thank you for attending. We want to make today's webcast as interactive as possible, so you can enter questions or comments in the YouTube chat area now, and we will get to as many as we can. We also received a number of questions prior to the webcast, and we will work in a few of them as well. Now I'd like to introduce our featured speakers for today. Dr. Matthew Walsh is a senior data scientist within the CERT division here at the SEI. His research centers on leveraging artificial intelligence to enhance cybersecurity and to usher in novel organizational capabilities. Next, we have Dr. David Schulker, and he's also a senior data scientist and a team lead and also in our CERT division. His research focuses on designing and applying machine learning and artificial intelligence systems, testing and evaluating these systems, and analyzing their safety and security. And now I'd like to turn it over to Dr. Matthew Walsh. Matt, all yours.
Great. Thanks so much for that introduction. As we said, my name is Matt Walsh. I'm a senior data scientist in the CERT division of the Software Engineering Institute. And my background is in computational neuroscience. And so that background has led me to a career in artificial intelligence. It's been especially exciting for me over the past 5 years to see AI to begin to realize its full potential. At the same time, it's been startling to see some of the failure modes and accidents emerging involving AI systems. And so in our work, in addition to developing AI capabilities, we think about how we can perform analysis to also ensure the safety and security of AI systems. And now I'll turn it over to Dave to introduce himself.
Yeah, thanks for that great introduction, Matt. My name is Dave Schulker. I'm former Air Force officer, and I'm in about my 15th year of doing quantitative research in national security since the end of my Air Force career. And I'm in my 3rd year on the CERT data science team at Carnegie Mellon University Software Engineering Institute, this great gig where we get to do applied research on some pure cybersecurity problems and then other problems that more broadly think about safety and security and test and evaluation for AI systems. So we're going to share some of those insights with you guys today. Really excited to talk about this stuff with y'all. Back over to you, Matt.
Great. Thanks so much. All right, so these are the topics that we're going to cover during today's discussion. And I wanted to start off by giving some background on STAMP and this way of thinking about accident causation. So safety engineering has a long history going back over 100 years. At that time, society's systems were mainly mechanical or electromechanical. And in that type of system, the primary cause of accidents was component failures, things like a valve getting stuck in an open or closed position, a hydraulic line rupturing, or a pump becoming inoperable. And so if this is your view of accident causation, accidents are caused by component failures, then the solution space is to increase the reliability of your components, to increase redundancy so that if a component fails, there's another component to take its place, or performing more frequent maintenance and inspection. Now, over time, our systems have evolved. And so today's systems include thousands or millions of lines of computer code. They're made up of subsystems, each of which is highly complex in and of itself, and they include emerging technologies like AI that transform the role of the human operator in the system. And so in these modern systems, a new source of accidents have emerged. And these are accidents in which all of the components behaved as intended, and yet they interact with one another in unsafe ways, giving rise to accidents. So to give a concrete example, this A320 aircraft runway occurred when pilots were approaching a landing on a runway that was short and wet. So those conditions are challenging, but they can be anticipated. In flight, the pilots disabled one of the aircraft's reverse thrusters. And as they approached for landing, they knew that the reverse thruster was disabled. At touchdown, the pilots pulled back on the throttle on the remaining engine. Now, this gave rise to a state that the system designers hadn't anticipated. The throttle was pulled back on one engine, but not on both engines. As a result, the spoilers didn't disengage, the auto brake didn't kick in, and the system entered an incomplete reverse thrust state. So one of the engines applied reverse thrust, essentially causing braking, while the other engine applied forward thrust, causing acceleration. And this caused the pilots to lose control of the aircraft and for the aircraft to overrun the runway. In this example, the control logic was executed exactly as it was coded. None of the sensors broke, none of the hardware broke. And yet, this accident occurred because of an unsafe interaction between the pilot, the software, and the hardware that made up the system. So in this case, the solution isn't to create components that are more reliable. There was no component in this system that broke. All of the components behaved exactly as they were designed. But instead, the solution is to consider the design of the system and to alter its design so that the system behaves as intended. STAMP is a way of thinking about accidents, and it's based on an extended model of accident causation. So STAMP can account for accidents that occur due to component failure, but it can also account for accidents that occur due to unsafe interactions between components, each of which is behaving exactly as it was designed. In modern systems, this latter cause of accidents, unsafe interactions between components, has become more prevalent. And so STAMP provides a powerful lens for analyzing safety in complex systems, including systems with AI controllers. And so now Dave is going to talk about one application of STAMP to prospectively anticipate the ways in which a system can behave in unsafe ways.
Yeah, thanks, Matt. So we wanted to open by giving you a brief overview of really the so what of where is the power of this technique coming from and how does it work in practice so that for potentially the people who are on the line who are unfamiliar with the technique or maybe want to know just what it's about and why it might be worth investing more time in, we want to give you the so what at a high level. So I'm going to go through the basics of System Theoretic Process Analysis, which like Matt said, is a prospective way to analyze a system throughout its design process and try to anticipate some of those hazards like the one in the accident that Matt talked about. We want to anticipate those hazards before they occur. So let's step through this real briefly. So the STPA model, the STPA process, which by the way, if you're interested, there's a handbook on MIT's website where the technique was created that will step you through all this information. The process begins not too different from a typical safety process. You begin by trying to identify the losses that you want to prevent. So if you think about a loss, what do we call a loss? In general safety vernacular, the loss is usually narrowly defined. It's usually where we want to prevent the loss of maybe an aircraft. We want to prevent loss of life. We want to prevent damage to equipment, damage to the environment, things like that. One thing that's a little bit distinct about STPA is that it allows you to take as broad of a lens on the losses as you want. So a loss in STPA can be anything that's important to a stakeholder. And why that's, so it could include broader things like loss of reputation. If you work for an organization and a system could cause embarrassment to your company, that could be a loss of reputation if you're a bank, for example. Or it could include things like loss of privacy, loss of security. And so as we were thinking about AI systems, this is a huge feature of STPA that's very helpful for AI systems. And then as we think about security analysis, this broader definition allows us to consider security because if we make loss of critical information or loss of privacy or something like that one of our losses, then every downstream step of the analysis is going to focus on designing the system to ensure that that loss doesn't happen. So this is a starting point. We're not thinking about systems right now. We're not even thinking about anything in particular. We're thinking about, we're designing the system. What is it that we need to prevent? This is also where your definition of safety and security comes from. So that if you say, well, what does it mean to be safe? What does it mean to be secure? At this stage, once we're done and we've consulted with stakeholders and identified our losses, then a safe system is a system that will not result in these losses. Go ahead and advance the slide, Matt.
Hey, Dave, what you're saying relates to a question that we received online. The question is risk management for failures or attacks in artificial intelligence systems the same as it's defined in the field of risk management?
Yeah, thanks for the question, Matt. So I would say that STPA itself is not a risk management technique, but that it fits within the realm of tools that you can use for risk management. And so if you look at, in general, when you think about risk management, there's the process side, there's the organizational side, all that kind of stuff doesn't really deal with STPA. But then when you get into trying to actually brass tacks identify what are your risks and how can you mitigate them, that's really where STPA comes into play. So for example, most international standards or national standards about risk have this phase where you're trying to identify your risks. You want to try to understand maybe what's their probability, what's their severity, and then what do I know about how I can mitigate those risks? And then, what is the mitigation cost? Is it worth it? So you try to ultimately make these decisions that manage risk. STPA will help with those decisions insofar as at this stage, we'll identify what are the actual risks that this system exposes us to with our set of losses. And then STPA, the technique, will allow us to understand how is it that the system could cause those losses and how can we mitigate it. And in fact, other hazard analysis techniques are listed in international standards exactly at that part of the risk management process. So it does interact. It is a very useful technique for risk management, even though it's not itself a risk management process.
Thank you.
Okay, so the loss state was very general. The stage of the process, we're trying to identify the things we need to prevent. What is a safe system? The next stage is to try to identify hazards. And what differentiates a hazard from a loss in STPA is the hazard is something that's within our control because it's a system state. So at this stage, I want to think about what is every state that the system could be in that would potentially expose me to a possible loss. And so, for example, in the case that you see with the cars on the slide, the loss that I'm trying to prevent is loss of life or loss of my vehicle or damage to my vehicle. But that's not necessarily, that's broad. That's not specific to my system. Specific to my system is my vehicle can't get too close to another vehicle or an object. So that's the system state that I'm trying to prevent. So typically you create a list of maybe 5 to 7 hazards, maybe a few more and some sub-hazards, which is outlined in the STPA handbook, that are, again, not specific to an architecture or a system. They are just the system states that expose you to losses. And then safety is if we can prevent all of these system states, then we can say that the system is safe. Next slide, please. Now, so here's where you get into the systems theory part of STPA. And this is what I'm calling on the slide the special sauce. This is where the insights to STPA really come from. The next stage is that you create an abstract model of your system called a control structure diagram. And you think about the behaviors of the system using system control theory as basically a series of control loops. So what I've got on the right-hand side of the slide here is an example of a control loop. And the key features of a control loop are you have a controller, which has an overarching goal in order to exert control on a controlled process. So it's hierarchical in the sense that the controller has authority over the controlled process. The controller is going to achieve that goal by issuing commands called control actions. And then the controller is going to know how to achieve that goal based on its interpretation of feedback from the controlled process on what is the state of the controlled process. And we'll walk through an example to try to help you understand how these control loops are really helpful for anticipating those complexity type safety security scenarios. But once you have your control structure diagram, essentially what you do is the next formal step in the process is you identify what are called unsafe control actions. These are actions where when would it be a bad time if the system issued this command to this controlled process? Or when would it be a bad thing if the system failed to issue this command? In other words, when would the system go into a hazardous state because it either gave the wrong command at the wrong time, or it failed to give a command at the wrong time, or if you look at the 3rd and 4th classes on the slide, potentially there's cases where maybe it gave the wrong command, or it gave the right command, but it gave it too early, or it was too slow, or it gave it in the wrong order, or potentially it applied the command, but it didn't apply it for long enough, or it applied it for too long. So if you go through all of these, it covers all the possible ways that a command could be unsafe. And then that's the backbone. That's our goal for the STPA is we've got to prevent all of these unsafe control actions, UCAs. All right, so I want to this was really helpful to me when I was first learning the technique. So I want to use a basic example that's going to be intuitive to most people. You think about driving a car, and we can have a simple control loop like what you see on the slide. You have a driver, you have a vehicle. The hazard that we have to prevent is that, like I mentioned, that car getting too close to people or objects. So the driver is going to give commands to the vehicle, which are simple: brake, throttle, steering angle. And then the driver is going to issue those commands based on feedback that the driver receives from the vehicle. So I know how fast my vehicle is going. I can see through the windshield potential objects that are in my path, other cars, things like that. So if, for example, if I'm driving on the Beltway and I see that I'm approaching another car, my estimated distance is decreasing according to that visual feedback. I have to interpret that information using my own process model. If my distance is decreasing, I'm potentially going to get too close to that object. Then I have a control algorithm, which is how do I respond, given that I understand that that's what's happening. If I'm getting closer to a car, I need to brake, and I need to brake a certain amount to make sure that I preserve that distance. And then I give the correct command. So here I've just given you an example of how system control functions as it's supposed to and prevents a hazardous condition. Well, what happens if we introduce more into the system? So if we go on and we introduce, say, level 2 autonomy. A lot of cars come with some amount of autonomy where the car can issue its own. If I set the car, if I enable it or disable it, it can issue its own steering angle commands, and it can issue its own throttle and brake commands. So let's introduce level 2 autonomy. So I've got a new controller here, an autonomous driver. That controller is going to potentially issue brake commands to the vehicle. And it's going to do this based on radar and potentially other sensor inputs to it. It has some process model for interpreting those radar and sensor commands. For example, it might even have a computer vision model, and it has to interpret those images and turn that into understanding of the world and objects and things like that. And then it has some algorithm for understanding when it's going to brake and how much it's going to brake in response to those inputs, right? So the autonomous driving can do, we have that little control loop, but then I'm the driver, I'm still in charge. So I can enable the autonomy, but then I can directly accelerate or brake, and then I'm doing that based on the same feedback. So the question you have is, now that we have a more complicated control structure, can this control structure enforce the safety conditions? Can this control structure prevent the hazard that we've been talking about? Or is there something missing from the control structure? And what you'll find, and if you've been in a car that has one of these features, go ahead and enable the slide, Matt, is that actually there's a missing feedback loop in the control structure that I showed you, and this is how it would work. You take this example of a level of autonomy that's trying to identify objects and then predict their movements and respond. So something that's more closer to fully autonomous. It could potentially misclassify objects. It might potentially misclassify a pedestrian as a vehicle or something like that. And if it does that, it's going to predict inaccurately the movements of that object because it doesn't expect vehicles to go perpendicular to your path. It probably expects them to either be stationary or going forward. So if that happens, then it won't necessarily brake, even though there might be a pedestrian or something entering the roadway. But if I don't understand the state of the autonomy, I might incorrectly, through my process model, assume that the autonomy is going to take care of braking. Therefore, even though I'm getting the feedback that I'm getting closer to this pedestrian, I might not brake in time unless I have the awareness of the status of the autonomy, which is why most autonomy designs have some sort of visual feedback available to the driver of what the autonomy is seeing, so that if I look down and I see, oh, the autonomy doesn't recognize this object, and then I see the object, then I can intervene to brake because I understand that the autonomy is not going to come into play there. So this is the beginning of how STPA works, and this is really the power of STPA, because in this whole scenario that I've laid out, nothing in the system has actually broken. No valves have been stuck, no tires have blown. But what's happening is we're trying to think through whether each controller in the system has all the inputs and information that they need in order to correctly apply the control actions that enforce and prevent the hazards from happening.
Hey, Dave, so the autonomous driving controller, this is potentially an AI controller. And the question was submitted, are AI components black or white box, and how does that affect your analysis strategy?
Yeah, that's a great question. And it's so you can see right here, the level of abstraction in the control loops that I have here is very high, right? I have a box for a driver, a box for the driver's process model. I have a box for the autonomy, a box for the autonomy process model. And so what this shows you is that STPA is already equipped to handle complex parts through this sort of abstraction. And so you might think, well, machine learning or autonomous component is too complicated to analyze, right? What's going on in there? It's got billions and billions of parameters and things like that. Well, the way that we handle that is we represent it as an abstraction, and then we try to understand, at a high level, what is the feedback available to it? How does it process it? And then what commands does it give? And we try to test and find out whether it's actually capable of enforcing the security and safety constraints that we need it to enforce. So it can handle black box. The driver, in a way, is a black box component, right? We can't model everything that's going on in a driver's head, but we can represent the driver at a high level of abstraction, and STPA already does that naturally. All right, so continuing on with the STPA process, we've identified losses, we've identified the hazardous states that we've got to prevent, we've modeled the control structure, and then we've identified when would it be a good or bad time for for each controller to issue the control actions. And then the next step is to walk through, and STPA has a very rich scenario development process where we can identify those sorts of cases of, okay, obviously it would be a bad thing if this controller issued this control action at that time. Why might the system do it anyway? And that's where the scenario development process comes in. The system might do it anyway if it doesn't know that that's the state of the control process because there's no feedback provided to it. Or perhaps it does know that, but its process model isn't rich enough or isn't mature enough to really interpret that feedback correctly. Or maybe there's a bug or something in the system where some other input or some other state will intervene and prevent it from taking the right control action. So the scenario development process is where you identify those glitches, like the kind in the accident we talked about earlier with the reverse thrust. We try to identify, okay, well, would there ever be a case where it would, have one engine going forward and the other one going reverse at the same time? And then we hopefully can anticipate some of those scenarios. Once we identify those scenarios, then we can rack and stack and analyze different safety fixes that will prevent them. And then those lead directly to safety tests that we can use to confirm that the mitigations for the scenarios were effective. And this is, by the way, a really important part of designing and developing autonomous systems, is developing a growing body of essentially safety tests so that you can do regression testing. As you modify machine learning models, as you modify autonomy components, you want to continuously test to make sure that you haven't if I fix something over here, I haven't made it less safe over there. And so STPA reveals what those safety tests need to be, and it helps you build that body of safety tests that you can use for regression testing.
Hey, Dave, we had a question in chat about how the concept of false positives and false negatives from data science apply to this example. So can you just talk a little bit about where false positives and false negatives would fall within this analysis?
Yeah. So the way that we would factor that in is we'd have to think about that signal. I assume, let's say, for example, we're talking about object classification. So those object classifications are going to get fed to some component in the system. Let's assume that there's some controller that relies on object classes as feedback in order to know when it should do something. So if there's some controller that's supposed to brake, for example, to avoid objects. So in order for it to know when to brake, it needs to receive that feedback. It needs to understand what objects are out there. So that's where the lens of false positives and false negatives comes in, is because when we go scenarios, we say, okay, what are some of the reasons why it might get incorrect feedback? And one of those reasons might be, well, what if it has a false positive? What if it has a false negative? And then we have to think about, well, can we design the system so that it's still safe, even in the light of false positives and false negatives, which we know are inevitable? So the way that it factors in is we represent that classification of objects through the control structure. We represent it either as feedback or as a command or as something in a controller's process model. And then through the scenario development process, we identify where those errors fall in, and then we identify mitigations so that the system as a whole still functions, still avoids the hazardous state.
Excellent.
All right, great. And then there's one thing before we go on I wanted to comment about is this probably started sounding pretty reasonable. We've got a few losses. We're going to identify some hazards. Then when you think about unsafe control actions and control structures, and there's 4 classes, and this control structures could get a little bit unwieldy. And then we need scenarios for basically all of the different types of UCAs. So this might sound like, and this is related to a question that we got ahead of the webcast, that this might sound like it's getting pretty labor intensive at this point. And I know you've thought a lot about that, Matt. Do you want to comment on, is this too unwieldy? Is this really labor intensive? Is this possible for the average safety analyst to do?
Yeah, so that's a really practical question. Just how time consuming and costly is it to perform an STPA? And so I think we need to contextualize that question first and say how timely and costly relative to what? So safety engineering is a demanding form of analysis. And when STPA is compared against other safety engineering techniques, it is less costly and less time consuming on average than other formal safety analysis techniques. The second thing to consider is if you don't invest in the safety analysis up front and discover the design flaws once the system has been developed and fielded, it is far more costly to remediate the design flaws once the system has been deployed versus discovering them from early in the design process. That being said, just what does it take in terms of hours and labor to perform this type of analysis? So to prevent the STPA from becoming prohibitively costly, you need to scope the analysis properly. Begin by talking with a stakeholder about what the most critical losses are that must be prevented, and then focus the analysis on the hazards that lead to those losses and the unsafe control actions and scenarios that can lead to those hazards. So you can kind of reduce the cost by bounding the scope of the analysis. The second way to reduce the cost is to use abstraction. So when we're creating a model of the system, that model doesn't need to contain details going all the way down to bare metal. We need to judiciously apply abstraction to limit the complexity of the system that's being analyzed. The third thing is to use software and other tools. There are tools available to help you to perform a more systematic STPA and to accelerate the steps in performing STPA and generating artifacts and documentation. And here's the last thing, and this has been kind of eye-opening for us. We've analyzed several different AI systems, and what we find is that there are a lot of similarities across AI systems. And so as we've built out this portfolio of STPAs, we find that a lot of those results generalize to other systems. And so it was most costly to perform early STPAs, but with each subsequent system that we analyze, we get a lot of cost savings from generalizing the findings from our earlier analysis. All that being said, to arrive at actionable insights, actual design decisions, and identification of test cases, we find that 2 to 3 people working from 2 to 4 weeks can kind of arrive at the point of having actionable recommendations. A complete STPA, of course, will depend on the complexity of the system and kind of the level of rigor applied. But within 2 to 4 weeks of analysis, we start to arrive at actionable recommendations and insights.
Yeah, that's helpful. And before we move on, I think there's another good question, and I think we're going to have to address this at some point, so it'd be great. I think it's a good time now, is the question of stochastic inputs. AI components, machine learning components are probabilistic models. They're statistical models at their core. And so they're going to be, unlike maybe some other deterministic components in the system, they're going to be sometimes providing from the same inputs, potentially different outputs. And so the question is, well, how does that factor into a technique like this? How do we address that with STPA? And I'll just give a comment on this, Matt, and you can react to it, or you can comment on it if you want, since you just addressed the last question. I think what it really highlights is that the process of identifying where those stochastic outputs expose you to hazards is where STPA really shines. Because if it's really true, we start with losses, and losses are not nice to prevent. Losses have to be things that are truly unacceptable. And so if I have a stochastic output and I can't guarantee that that stochastic output is going to 100% be effective, and it might lead to a hazard, which might lead to a loss, then I need to design a system that there's some sort of fail-safe that protects me when that stochastic output is wrong. You might think, well, maybe we could measure the likelihood that that stochastic output is going to do me wrong. I wouldn't recommend that, A, because when you deploy the system, I'm not sure that your probabilities from testing are going to generalize. And B, we're going to talk about security in a bit. And then in national security context where you're worried about adversaries, well, the probability that it happened in testing is not going to be the same as when you have adversaries actively trying to undermine your system. So I think you have to use STPA to recognize where those stochastic outputs introduce UCAs, which then introduce hazards. And then you've got to design the system so that you prevent those. So it is STPA is actually shines in light of that. What do you have any reactions or comments to that, Matt?
Yeah, the final thing that I'll add to that, so within a system, the AI component is just one controller. There are other controllers. And so as we seek to make the system safer, we can focus on that AI controller and trying to reduce the probability that it will produce an incorrect output. But we can also look to the other controllers that make up the system. And we may find that there are mitigations involving other controllers that, in this language, eliminate the possibility of the hazard occurring, even if the AI controller produces an incorrect output.
Yeah, I mean, a good example might be if you think about automated safety features in cars. You know, if I'm driving, again, using that example, my reaction time to cars in front of me is stochastic. You know, sometimes I'll react quickly, sometimes I'll take longer, but then we can build other features into the car that will make sure that the system itself remains safe in light of my potential stochasticity and how quickly I can react. So in other words, a safer design with those features won't depend on me having super fast reaction time. It will allow for me to have variable reaction time, and it will still hold up. I think that's an example of that. Okay, I want to get to the examples that we have later on. So let's press on. I just want to make one quick comment about security, and we'll talk about security as we go through the examples that you can see. But when you think about applying this to security, the designers of STPA made a really fundamental insight that I think is really interesting when you think about it, which is that when you think about safety and security are kind of dual problems. The safety is we're trying to prevent the system from entering a hazardous state and causing a loss on its own. But if you think about if you're an adversary, you're essentially trying to solve that same problem, but in reverse. If you're an adversary, you're trying to cause the loss. And the way that you're going to cause the loss is by trying to force the system into a hazardous state. So the same control structure diagram with all those control loops with control actions and feedback, the same control structure diagram that is designed to be safe, we can use that to try to analyze whether it's also designed to be secure. The primary difference is when we think about scenarios, and if you go on to the next slide, Matt, when we think about scenarios and the security and the safety case, we were trying to think about, is there any way where the system, some combination of inputs and some combination of commands could result in a hazard? In security, we'll put on the adversary hat and we'll try to think, okay, is there a way that if I wanted to cause this, that I could cause this? Then that'll lead to another set of scenarios that cause UCAs, and then another set of requirements, security requirements that we can use to prevent attacks. And the final, I think, really good insight about this duality between safety and security is that anything that if we can prevent a UCA completely, then we've not only prevented the safety scenarios, but we've also prevented the security scenarios. Because if the system can't issue that UCA, then that means that an adversary can't cause it, just like the system can't if they can't do it at all. So the controls that we put in to make the system safer might make the system more secure. The controls that we put in to make it more secure might actually make it safer. And using the same control structure, the same way of reasoning about the system has real benefits for trying to achieve a more holistic solution to the problem. All right. Yeah, sorry, still me. Let's talk about the first example. If you want to go on, we've got a couple of different examples, or I've got one example of STPA, and then we're going to talk about CAST, which is a different technique, still grounded in systems theory and STAMP. And so this example comes from something that was presented at the MIT STAMP conference. It's a public paper. You can see the link to the paper if you want to read more about it. And the example is they did a system theoretic process analysis of an autonomous aircraft before testing it. So this wasn't necessarily an analysis to make sure the aircraft is fully safe to be deployed. It was making sure that the aircraft was safe enough to test, live fire test. So I think a lot of people who work in the T&E community could probably relate to this, whereas particularly national security weapons testing, before we can even move to a live test, we need to make sure that the system is sufficiently safe. So the idea was we had an agent that could autonomously fly an aircraft, And that agent was trained with reinforcement learning. And so the agent would read all the feedback from the flight computer of the UAV, and then it would provide command inputs, pitch, bank angle, and thrust. But it's a bit of a black box. We don't really know, other than the fact that we understand something about how it was developed and trained. We don't really know the state of that agent or how it thinks or anything like that. So before we test it, we want to put essentially guardrails around that RL agent to make sure that it doesn't do something unsafe to crash the UAV. So they had a few different guardrails. They had a set of command limiters that would just clip commands if they were outside of some boundary that was considered to be safe. So if the reinforcement learning agent put the throttle too high, or it put at too extreme of a bank angle or something like that, then the command limiter would just clip the command and the aircraft would only go up to the limit. And then the other thing is that anything, if the aircraft either got too slow or too fast, or if it hit a max or minimum altitude, then the system would automatically terminate the autonomy and transition control back to a human operator. Okay, so the question is, can we use STPA and try to figure out whether this is safe or whether the system could still get itself into a hazardous state? So if you look at the gray box here, the loss we're trying to prevent is we don't want to lose the UAV, we don't want to damage the environment. The hazard is, well, in one case, one of the hazards that they looked at is the UAV can't get too close to the ground, can't get too close to objects. So then we have to think through, all right, what are the command inputs that would cause the UAV to get too close to the ground or objects? What are some of the situations with the roll rate or the bank angle or the thrust that would cause the UAV to get too close to the ground? And then we can think about scenarios for this. Why would it issue that? Why would it issue these commands on its own? And potentially, how could an attacker cause these commands to happen? So if you go on, Matt, I have another example of this.
Just a second before we do so, a question came in, how does STPA differ from traditional methods? And to take this example that you've provided, so again, the main difference between STPA and traditional methods is that traditional methods assume that the accident is caused by a component failure, whereas STPA and STAMP also permit the possibility that no component has failed, but the system is designed in such a way that the components can interact with one another in an unsafe way, giving rise to an accident. And so if you applied a traditional method like fault tree analysis to this system, it would not anticipate this accident mode. And that's because in this accident mode, the sensors are all working properly. The software is, there are no bugs in the software. The hardware is all functioning as it is intended, but the system is designed in such a way that this unsafe interaction between controllers can give rise to an accident.
Yeah, so this is one of the scenarios from the paper where everything I presented to you, it probably sounded reasonable. It sounded fine to me. I thought, okay, command limiters, clip the commands when they get out of bounds, should be fine. But when they did the system theoretic process analysis and they analyzed this control loop, they found out that there were a few key problems. One of them is that the agent is not necessarily aware of the existence of the command limiters because it was just trained to fly the drone or the UAV. It wasn't actually trained to interact with the command limiters. And then the second flaw that they found is that the command limiters only apply to the individual commands in isolation. They don't apply to combinations of commands. And so they found that there were combinations of commands that wouldn't violate the command limiters, but that would still potentially put the aircraft in a state where it wasn't controllable. And then this interacted negatively with the fact that the agent wouldn't necessarily be aware that that's what's going on because it wasn't trained. So basically, if the system got slow enough and it achieved a bank angle that was within the limits of the command limiter, it would start losing altitude. And if it was in that state, there was no way to provide enough thrust and enough pitch control to actually maintain a stable altitude. So what would happen is if you look at the control loop on the left, the agent would recognize that altitude is decreasing, and the agent would try to increase the pitch and increase the thrust. But then the command limiters would be clipping those commands because the command limiters don't allow you to go beyond certain limits. And then all the agent would see is this doom loop. I'm still decreasing altitude, so therefore I need more pitch. And then the command limiters would say, you can't give any more pitch, and the agent wouldn't be aware of this. And so essentially what the UAV would do is it would turn steeply, and then it would lose altitude, and then it eventually would hit the minimum altitude, and it would abruptly transition command back to the human operator. So the human operator inherits a UAV that's already falling towards the ground, and it's in a steep bank angle. And so this is an example of a scenario that you wouldn't necessarily see, the overall design seemed pretty plausible. But when you actually think about, okay, what situations could you get yourself in where you wouldn't violate any of those command limiters, but you would still potentially be in a hazardous state? And then STPA identified this ahead of time.
Mm.
So what they did was they had to put more controls in to sort of more controls beyond just the command limiters to try to prevent the UAV from getting in these sorts of situations. And then just to give you, they didn't talk about security in this particular paper, but we can reason through security using the same way. And so this is how it works. We can think about that same, we can think about a similar control loop where anytime the control of the UAV has to go from the autonomy to the human pilot, you're going to have this transition. And you have to make sure that the transition itself is a safe process. And so the UAV in this particular case was designed so that anytime a transition was going to take place, the UAV had to stabilize itself before the transition could happen. So it would go to zero roll, it would go to zero pitch, it would stabilize the speed, and then it would execute a handoff to the pilot. So, and it's going to do that anytime the transition conditions are met. Like I said, minimum altitude, maximum minimum speed, those sorts of things. So a UCA for this system, safety or security, doesn't matter. A UCA for this system would be, what if the transition maneuver does not transition control to the pilot when there's no autonomy? That's what we have to prevent. That's one of the things we have to prevent for safety. And so from a security lens, we can think about, okay, if I was an attacker and I wanted to cause this, how might I cause it? Okay, well, if I know that the system has to be stable before it will transition control to the pilot, then is there something that I could do if I had another aircraft in the air to prevent it from getting stable, right? Could I perturb the air around the aircraft to delay its stabilization? And if it did that, then I essentially caused this UCA. I prevent it from transitioning control to the human pilot without any kind of cyber access to the drone or anything. I just did that by perturbing the environment. Potentially, I could use something like an RF attack to prevent the handshake, because obviously it can't transition control to a human operator unless it has a two-way handshake with the human operator's control. Or to get deeper into STPA, if I had some kind of access in the system, I could think about ways that I would change the inputs that would cause the UCA. So potentially, the system is going to transition control, let's say when it hits minimum altitude. Well, if I'm an attacker and I have some kind of access to the system, what if I don't actually need to change the control? All I really need to do is change the sensor readings. Maybe I delay the sensor readings so that it doesn't actually understand what altitude it's at. Or maybe I spoof the sensor readings. So in this case, I don't actually have to have command of the UAV. I just have to be able to manipulate its understanding of its state, in this case, altitude, in order to be able to cause the UCA and therefore cause the hazard and the loss that I want to cause. So this is just give you a little bit of an introduction into how you can use the same type of reasoning to identify security flaws that we used a second ago to identify safety flaws.
Excellent. So to this point, Dave's been talking about system theoretic process analysis. This is a prospective way, as you are designing a system, to anticipate the ways that the controllers can interact in unsafe ways, giving rise to accidents. There's a complementary approach that we can use called causal analysis using system theory. And this is a retrospective approach. In the case of CAST, the accident has already occurred. And now we ask ourselves, how can we learn from this accident? And importantly, rather than trying to assign blame, how can we extract a generalizable set of lessons that we can apply to increase the safety of other systems in the future? So traditional accident investigation practices are based on this linear model of accident causation. There was some root cause that led to the accident, the first domino in the sequence falling over. Traditional accident investigation practices ask, what was it that failed? What was the root cause that led to the cascade? Causal analysis using system theory, or CAST, is based on the same underlying system theoretic view of accidents. So the goal of using CAST is to understand the interactions between the controllers that make up the system, the feedback loops, the organizational structures, and other factors that contributed to or allowed the accident to occur. And so CAST answers a slightly different question. Rather than asking what failed, we're asking, why did the system allow this to happen in the first place? Okay, so STPA is prospective. It identifies all possible loss scenarios and then traces those down to the hazards, the unsafe control actions, and the scenarios that can give rise to them. In the case of CAST, our task is a little bit easier. The accident already occurred, so we know what the loss was. The pedestrian was struck by a car and was injured. We can analyze the accident to see what hazards, unsafe control actions, and scenarios led to that loss occurring. And now the focus in CAST shifts to looking at the control structure and saying, what is it about these controllers and the ways that they interact with one another that allowed this accident to occur? Okay, so just as Dave walked through some examples of STPA findings, I'm going to walk through 2 examples of CAST findings. So the first one carries forward this example of an autonomous vehicle. And so this is based on a real-world incident. In 2019, there was an accident involving an autonomous car striking and killing a pedestrian. And so what happened, a pedestrian was pushing a bike, and you can see in the diagram there along a sidewalk, and then they crossed the street at an unmarked location. Now, in the lead up to this accident, the autonomous car detected the pedestrian from hundreds of meters away. Now, it turns out the computer vision model on the vehicle was trained for multiple classes, including a pedestrian class and a cyclist class. Now, in this case, the pedestrian was pushing a bike, and so the computer vision model switched between those 2 labels, pedestrian and cyclist. Each time that it switched labels, it discarded the positional history, so the vehicle didn't recognize that the pedestrian was on a collision course with the vehicle. Now, about 6 seconds before the vehicle struck the pedestrian, it switched to reliably predicting the pedestrian class. And so the vehicle recognized at that point that the pedestrian was on a collision course with the vehicle. But it didn't stop immediately because the system was designed to have a 1-second delay to prevent false alarms. And so another second passes, and now the vehicle is very close to striking the pedestrian. At that point, the vehicle did apply brakes, but it didn't apply maximum brake force because the system was designed to use gradual brake force to avoid exposing the driver of the vehicle and the vehicle itself to extreme braking. So the vehicle began to apply the brakes, but it was too late at that point. It struck and killed the pedestrian. And so as we analyze this accident, we can identify kind of all along the way alternate design decisions that could have been made to prevent this accident from occurring. If you'd like, you could take a moment and type some of your ideas into the chat. What are some of the alternate design decisions that could have been made that would prevent an accident like this from occurring?
Yeah, Matt, you did a really good job of highlighting, I think, that, if you're just trying to prevent one particular accident, then it may seem straightforward, but oftentimes the accidents that result are the result of deliberate design decisions that were meant to prevent some other accident from occurring. And so, like you said, the delay to prevent false positives sounds like a terrible design decision, but it was made on purpose in order to prevent other accidents where if the car was constantly slamming on the brakes, not only would it be injuring the drivers, but if it was false positives, it would be causing accidents. Potentially another car would hit that vehicle from the rear end. And so you kind of don't, there is no, you're trying to optimize along a complex space with a lot of potential hazards. And so CAST is useful because we're trying to identify, okay, why did this accident occur? And then is there a better control structure that could prevent these sorts of things in the future?
Yeah, exactly. And so some of the ideas that kind of fall out of this retrospective analysis, if the computer vision model is classifying multiple objects, it should retain positional history from each of them. If the car had done that, it would have recognized that the object was on a collision course with the car. Don't prioritize, don't avoid extreme braking when you are about to strike an object. Don't include this 1-second delay to apply brakes when an object is on a collision course. In retrospect, we can kind of see how all of these decisions led to the accident, and they give rise to some recommendations and lessons that can be carried forward to other autonomous vehicles. Okay, so now to pivot to a second kind of security-focused example, in 2025, Anthropic reported the first AI-orchestrated cyber espionage campaign. And so in this attack, a nation-state actor used Claude Code to attack more than 30 global targets. Anthropic analyzed the attack and concluded that 60 to 70% of the actions were conducted by autonomous agents requiring minimal human oversight. And at the height of the attack, dozens of actions were taking place each minute. So as they designed this system, Anthropic anticipated that adversaries would attempt to abuse it, and they built certain security measures in place. So for example, the model was fine-tuned to reduce its propensity to release harmful information, like steps in a cyber attack. And the system included guardrails to detect and block suspicious inputs. At the time that the system was deployed, it was configured properly. The model had been trained correctly. The guardrails were in place. And yet, this attack was effective. So what went wrong? Well, the attacker took advantage of the propensity of large language models to try to be helpful. And it included in the prompt, I am a security researcher attempting to create and defend a system. Additionally, the attacker decomposed the campaign into smaller, discrete steps, none of which looked suspicious, and issued them to separate Claude agents to bypass the guardrail. And so as we talk through this attack, there are certain alternate design decisions that become immediately evident that if they had been in place, would have prevented this attack from being successful.
Yeah, I thought that attack, Matt, really highlights that AI sort of feedback guardrails, the sort where you try to incentivize language models to do the right thing and then to not do the wrong thing and to refuse bad requests. That at a certain level, that's not enough on its own, because at a certain level, cyber security behaviors or cybersecurity requests are really indistinguishable from cyber attack requests without more information about the identity of the person using the system. So when if we think about not just the large language model, but the system as a whole, well, we have other ways of confirming someone's identity before we give them access to different types of systems. We have components, we have identity verification techniques in cybersecurity that apply. So the situation is like, well, if reading the prompt is not enough for me to really confirm your identity, whether you're a cybersecurity person or a cyber attacker, then the only way that there is a way to prevent these types of attacks, but you have to think about the broader system. We need another way besides just, does the prompt sound malicious? We need another way besides that to confirm the identity of the person before we're going to allow it to execute, if we want to truly prevent that hazard. And I think this is a good example. I wanted to throw a question your way, Matt. We got a good question from Jonathan. I think this is maybe a good time to ask it. Do you think, based on your work with STPA, are there any big picture implications that you would share about the implications of using potentially open source software versus proprietary software? In this case, we're talking about an attack that used proprietary software, or potentially using open source software versus developing something in-house, developing your own software. Are there any general ways that you feel like STPA or the cast of some of the AI incidents would yield insights on that question?
Okay, right. So I'm going to partially answer that and then throw it back to you, Dave. So when we think about ways to attack an AI system, there are kind of two major classes of attacks to think about. The first involved providing unsafe inputs to the AI controller, and the second involved trying to essentially give the AI controller an unsafe process model. So when we talk about using open source packages, maybe it's a set of model weights, maybe it's a pre-trained model, maybe there's additional software to support the model's architecture. The risk in taking that open source package and moving it into our system is that we may be giving our AI controller an unsafe process model. The other thing that I'll say before I give it back to you, Dave, is even if the attacker doesn't have control of the AI component, we've been kind of surprised to realize all of the different ways that the attacker can provide unsafe inputs to the AI system. So even if the attacker doesn't have a way to directly affect the AI controller. A creative attacker can find lots of ways to provide unsafe inputs to the AI controller to cause the system to behave in unsafe ways. But yeah, Dave, what other thoughts do you have about incorporating open source libraries versus proprietary?
I think there's the AI lens, which is what you were commenting on, and then you can take a step back and say, well, all of these AI controllers are implemented in software, and so there is the general software lens. And so you think about if I'm going to use a proprietary component versus an open source component, where is that going to be hosted? How is it going to communicate with the rest of the system? How much am I allowed to know about that system's process model? Potentially, I can know more if it's open source, but if I develop it myself, then I really can know more. And so I think you have to use the systems theory lens, potentially think about the general cyber elements in addition to the AI elements to think about, well, what's the optimal. But the great thing about STPA, where it comes in, is we're not thinking about this in the abstract. Like, is an open source philosophy more safe and secure than a proprietary philosophy? No, what we look at is a particular system context. These are the losses that I have to prevent. In order to prevent those losses, I have to make sure the system doesn't get into these hazardous states. And then with respect to that context, you might make a different decision on open source, develop it yourself proprietary because of your particular losses that you have to prevent. So STPA really helps you focus in on your problem and the losses that are important to your stakeholder, instead of trying to do some research survey and figure out, okay, well, is an open source philosophy, or an on-prem or whatever, like which one is more safe and secure? So there's that element to it. It's like general cyber and relevance to your particular context that STPA is going to help with.
Excellent. So we wanted to end by offering some of our key takeaways from our experience using system theory. Our first observation is that in modern complex systems, accidents may occur even if no components fail individually. And so in complex systems, including ones with AI, this system theoretic perspective is a powerful lens to prospectively identify the ways in which accidents can occur. Our second observation is that STPA is an effective method for identifying these failure modes, but it also gives rise to actionable insights, actual system design recommendations that can be made, and test cases that can be used to assess the effectiveness of the mitigations that you implement. Third, and I think this was a great point that you made, Dave, STPA isn't just about safety. Typically, safety and security are treated as separate concerns, but they really are two sides of the same coin. And so STPA gives us a way to understand how the system's design can give rise to accidents, but also how it can be attacked. And so STPA can be used to develop mitigations that are effective against accidents, attacks, or both. Our fourth finding is that retrospectively, after the accident has occurred, system theory gives us a set of methods to learn from those accidents, not to cast blame, but to take away a generalizable set of lessons that can improve the safety and security of future systems. And our final observation is that, and through interacting with many different stakeholders, organizations can adopt this approach and use it to enhance the safety and security of AI systems.
One more question for you, Matt, before we close. Do you have any thoughts on trying to quantify the real world mission impact? This is based on a question that we got ahead of the podcast, and I wanted to make sure that we addressed it. Trying to quantify the real world mission impact of actual attacks and trying to figure out if that potential impact is enough to justify modifications. And in particular, when you're making big trade-offs about how powerful an AI component might be, but then the risk that it might introduce, how do you decide whether those mitigations, whether using the component is justified based on those real world impacts?
Yeah, and so I'll just kind of share one example. So at a recent workshop, there are many talks about aircraft accidents, and those tend to be high profile because there are lots of people involved. But if you also look at something like medical decision-making systems, these are systems that affect thousands or hundreds of thousands of people. There are examples of such systems making accidents or being attacked in subtle ways, which over time affect the population at large. So this is not, merely a hypothetical that AI systems will make mistakes and that AI systems will be attacked. There are real world examples of these things occurring and of them having effects kind of at a societal scale.
Yeah, that makes sense. And really highlights that it's not theoretical at this point. We have enough data to be able to start to reason about these things. There's one more question I just think it's a great question. I think it would be great to address. It is with the possible of how many subsystems you potentially have going on, any of which, so if we think about agentic systems or layers of guardrails, any of these systems could potentially be the root cause of the unwanted behavior. So how do we mitigate? How does STPA help you mitigate those kinds of system-wide issues? So I have a comment, and then I'll give you a chance to comment, and then after that, we should probably turn it over to Shane and close. But I think the great thing about STPA is that it goes back to that core insight of does failures cause our accidents, or does complexity cause our accidents? And STPA is naturally help you to understand that it's equipped to help you understand when I add complexity, then I open myself up to more potential complexity interactions that could lead to hazards, right? And so potentially, if I have an AI component, I could have 10 other AI components that are meant to supervise that AI component. But STPA really helps you see and analyze how those other components are now introducing other risks because they can give commands, they can give unsafe commands, and then I have to monitor their state as well. So then should I have more overseers for them? How many agents before the system becomes safe? Well, you reach a point where you think, obviously, we need to simplify the system in order to be able to guarantee that it can behave in a predictable way. So STPA helps you manage that complexity, I think, uniquely among the different techniques. Do you have any thoughts or piggybacks on that, Matt?
Yeah, no, that's been my experience as well. So I just want to thank the audience for all of the participation and all the great questions that were submitted during the webcast and in advance. Dave and I's contact info is up on the slide here. So we have resources that we can share on STPA. And if this is a method that you're interested in exploring your organization, feel free to reach out with us and we can share additional learnings. All right, turning it back over to you, Shane. Thank you. Have a great day.